streaming, and hopefully this actually started streaming. Let's see. Okay, I will check it later. At least it's recording. So welcome to which course? This is the Sensors and Interfaces course. As I said, I will be changing the this web page accordingly to that plan sometime this week, not today. But anyways, the anyways, what the whole thing is all about is basically to give you some sort of experience on sensors and how to use them on microcontroller or embedded controller the environment. Okay, and target group is anyone who wants to know about it. Okay, so but anyways, the smart system students usually don't come here because we also have the same course given by different teacher on those fall semester, I think. Is it the same or no? It's a little bit different flavor. It's a different flavor. It's the about the physics and sensors and that kind of things. But anyhow, this also actually combines a couple of things. Some fundamentals of the sensors, but especially how to interface them with a microcontroller. On the smart system major, there's plenty of exercise how to interface anything with the microcontroller environment, but this actually goes through one way to do it. Smart way, I think. Okay, as I told you, originally Kim was also going to be involved with the course, but with these resources, no. Or actually with this number of students, no. So you have to cope with me. Good luck. Yes, you have a question? He was going to teach the labs. Yeah, but I will be doing those labs now. Okay. So enrollment. Metropolis students, you have already enrolled using OMA. You also have enrolled, yes, good. Then Open University students, email to me. Yeah, excellent. So basically, today we start with the topical lecture and then continue with the lab tutorial. And the remaining time, so that's why we have this 6-hour time slot here. Basically, first I go through a couple of sets of the show here. 2 sessions or 2 acts on this show. Act 1 is for the lectures. Today I'm going to is going to a lecture normally, but next week forward it will be a video of the last year, which you should watch before coming here. That's the whole idea of flipped classroom. Okay, and then the tutorial for the lab, and then you will start working. Our environment actually is right here. Programmable system on chip 1 evaluation kit. Excellent, you have your own. So this is the best microcontroller ever. If we are talking about 8-bit controllers. If you have been using Arduino, you probably never use it again after this one. Seriously, this is the best. Yep. All right. So, but the topics for the course are more or less there. So today is more about the introduction and going through the basics of fundamentals of this environment. Then next week is more about the sensors. Then data acquisition, which is, well, that's basically the ideology of when to take the samples, what you have to do for the data before you can take the samples and such kind of thing. So it's not, it's easy, but it's not straightforward. You just need to go through those. Then digital interfaces. Well, data acquisition is more like A to D conversion. And then the digital sensor interfaces, meaning just these serial buses, mainly 3 different serial buses, what are commonly used on different kind of digital sensor circuits. Wireless communication, actually that was one part designed for Kimmo, but since Kimmo is not teaching, I need to take a look at some of my archives and then look at if we have the equipment. Kimmo was going to, he was planning to do the LoRa network, which would have been a really nice addition to the course, and also good material, you know, kind of guinea pigs to test how this teaching material goes. But anyways, it was just for that reason the LoRa network, but now we actually have some freedom of choice here, as long as I can find the material of what I already have. Okay, and then the last but not the least, calibration. What calibration actually means. Yep, question, yes.
No, I was talking to you. I was asking you. I thought you were asking.
No. Okay, so, yeah, and this is actually the home page, which has everything for the course, what you need. So on OMA there's only the link to this one. And then if I have some announcements, I will go and send them through the OMA workspace. But otherwise, OMA has nothing on it. So each session actually have its own page here. On the home page, basically, there's also this online scoreboard. Okay, as you can see, I already marked some crosses and stuff. It's not updated yet, but it will be updated shortly. And basically we have exercises 1 to 8, except that exercise 6 to 8 is just one single exercise. This might actually change because of I'm doing it all alone. But anyways, fundamentally you have the programmable system chip environment as the first one. Then we have the A to D conversion exercise. Then there's sampling. Then serial communication. And then, wait a minute, USB. I need to take a look at if this actually is worth of a full exercise or not. But anyways, we will have the exercise for calibration. Okay, so those are the exercises, and whenever I have assessed an exercise, I'll immediately mark it here. So there's nothing on OMA until the course is finished. Okay, and basically this will start counting the points. The total number of points may actually change, but the percentage is which matters. So you need to get 40% of the points in total to get grade 1. So yes, you can also play with it. If you really are, you know, take only one, then you take the first 2 exercises, 10 points each, and you're done. Easy. But if you are heading for a better grade, and probably you are, Otherwise, you would be on much easier course. Then basically 90% is the limit. The 90% of points is the limit for to get the best grade 5. Okay, which means that you need to score quite good points. Okay, but this is most of these exercises they are either done or not done. So it's quite simple to get the highest grades. You just follow the workflow, and there's a couple of kind of tricks. For example, on returning the exercise, you having on the DSP course, right? Did you attend that DSP? No.
I did.
You did, yeah.
The B-side design.
Ah, yeah. So if your link to me does not open, it automatically reduces the number of points by 1. If there are 2 links which are not opening, okay, okay, yeah,
Simple, but
yeah, it's very simple, yeah,
turning in stuff.
yep,
Share it won't work.
yeah, yep. It's a good idea to check them before, yeah. Check them before you return them. No, okay. Okay, video stream. Actually, I could start that one. Would you click that one to see if our video stream is working? It isn't. Click on it. It might actually be just the. Okay.
Yeah.
Click on it.
No
It
guarantee
might
though.
actually be just the,
This is very low.
Hey, wait a minute. Yeah, it's working. It's working. Good. So, yeah. Video streaming is working. So I try to put everything online as I speak here, but this is low budget production. No guarantees. I'm also saving the stream, the videos clip. So actually, I download that video clip to the server later on. So for later viewing, that it hasn't failed yet. Keep my fingers crossed. Okay, then also mentioning about that the Creative Commons license. Okay, you know what that means. So basically, no commercial use. If you use it for commercially, I will sue you. Okay, and get your money and your house. Yeah. Okay, and share alike, meaning that you can distribute this one to your friends if you need, or take parts there. Just keep all the copyright notices as they are, and that's fine. I'm already paid for the job I do. I don't need more from that, unless you try to make profit. Yeah, that'll happen. I know this material is really great, but it's not that great. Yes, question.
Is there any prerequisite of this course?
Hmm?
Any prerequisite? It means I know something previously I do, because I have no class anything like this sensors interface.
Yeah, well, you will learn. You will learn a lot. Okay. So, don't worry, you'll be okay. So, let's start the first lecture, unless you have something in general about the course. No? Good. Okay. Then, oops, let's open this one on a different page. So, yes.
Do I have to be logged in to my Google account to see it? Because being not logged in, I can't see the presentation.
You cannot see the presentation. Okay, I need to make the change there. I thought that there was a permissions, but I need to just change the permissions. I probably should do it immediately. Otherwise, I might actually
The other
forget
ones
it.
are working, but the first one, we don't ask permission even with the
Slides. I see. Yeah. Share. Link sharing, allow external access. Done. Now it should open. Does it open?
Yes.
Excellent. Good. That was the only file I didn't, fix. Okay. This is the short introduction. I think this was also more about the this overall introduction. Okay, this is a good picture actually. Where's the beef in this course? So what we are doing now is we are concentrating on a black box, which is between the sensor senses the environment. That's as simple as that it is. But then you need a black box to get it to anywhere else. In our case, we are concentrating on PC, but PC can be anything nowadays. It can actually, the black box can already interface it directly to the cloud. Yeah. Okay. So, there are some good supporting material available. That's not the only one. The sensors, if you actually go to the e-library and take a look at how many books there are, even on the e-library, on the topic of sensors, you will find hundreds of them. But this I found actually quite nice. It's I think the writer was somehow, how funny it sounds, an engineer who can write. Okay, yeah. So it's very clear. It goes through the fundamentals and basically it has everything what is needed if you want to know more about the sensors themselves. Okay. And also, your Metropolia students, use your privilege actually to borrow them from e-library using your Metropolia account. It's all paid by the Finnish taxpayers' money. Okay, and about the piracy, there are plenty of books also that PDF files somehow has downloaded somewhere. Don't use them. They are usually pirate copies, so think of those guys who are trying to get some extra bucks for their living. I know some of these authors, and believe me, any physics or engineering book writer is not a millionaire. There's no such thing. Okay. A motivation. I don't need to motivate you, but I'll go through this. Anyways, this is so funny. So this is practical, useful topic. Yeah, it's practical. So basically, anything is monitored nowadays. Sensors are everywhere. So why wouldn't you make your own monitoring system somewhere? Why not? Of course, you can go to eBay and buy it, but much cheaper. But why not to do it? Okay, mandatory. You may need it. Well, not really. This is really some of these optional courses. They will be part of your degree or your the exchange studies. But anyways, it's mandatory nowadays. Living in peace. Interesting. Yes, that's the best motivation of all. For example, we could go through I think I have an example of where to use photo interrupters. Okay. And basically, interesting to find out sensor systems actually work. Yeah, it's fun to know things. Or then, if you are into games, how about making your own game controller instead of buying from eBay? Your own wouldn't probably work as nice, but you made it. Okay. Then the prerequisites you were worried about. Fundamentals of engineering physics. Good. Fundamentals of C programming. Done. Right. Good. Y'all are good. So basically this is really fundamentals. The embedded C programming has some peculiarities by itself, but here we are not going to find details. There are a couple of things we need to do, say a little bit more detail, like interrupts, how to handle interrupts. But nothing to worry about that. It is quite straightforward thing what you need to do, and it makes a lot of sense when I teach it to you. No magic about it. Yeah, and topics we went already through, so enjoy the show. There's also the introduction. Whoa. Okay, this is I copied actually some material from some other. Oh, okay, I have been updating a wrong sheet, I see. We don't have a study trip on this course. We will have study trip on the programmable system chip design course. And then this one is the syllabus of sensors and interfaces. But anyways, let's see, do we have also some other thing? Okay, about the, yeah, I need to update this anyways. About the environment or hardware we are using, that kind of thingy. Programmable system on chip, one evaluation kit from Cypress Semiconductors. There is a short story why I like this a lot. Year 2000 and something, I had a great idea. Actually, that was me and Kimmo who had the great idea. How about making some electronics for lures, fishing lures? So there are also some of those available on internet. But, well, why not to make your own? Because, well, good reason is that none of those internet electronic lures actually work. They have serious issues, like toxic batteries. That's a serious issue. Okay, so we started. Now I should actually, for this one, change my view a bit. Adjust that one. Okay, good. Electronic lure, and even the first version had everything on it what I wanted. So first there's a printed circuit board. There are also some of these hobbyists have done their own by soldering directly the components. I guarantee it's not worth of it. So basically, electronic printed circuit board, which looks a little bit like the cross section of a lure. And now I'm talking about the wobbler kind of lures, which are the ones with the plate, and it goes like wobble, wobble, wobble. Okay. And if you take a cross section like that one, actually, you can make that shape printed circuit board quite easily, and just mount a microcontroller and couple of LEDs there. One here, another maybe here on the printed circuit board, And basically, when the printed circuit board goes back there, it goes here. And then you can use this and that to get the power to charge the battery, which is inside and not that toxic. Okay, so basically you can put your battery inside of that lure underneath this printed circuit board, and that's the chip, and the LEDs actually go out like that, for example, and there you are, voila, an electronic lure that actually blinks lights. That's not yet done. The real catcher actually is that in addition to the battery, there's also a vibrator motor from a mobile phone. And that's the real thing, what makes the predatory fish hit the target. They are always looking for a easy prey, at least in Finland, in Finnish waters, cold water. And the northern pike is actually the main catch in Finland, and that always goes into injured fish. So it actually, when this one goes by that plate, it makes quite sinusoid wobble. There's nothing really good, really catchy about it unless you took some, do some lively kind of things with your rod. Okay, this actually adds something here. It resembles a fish that is already on a hook, a small fish that is already on a hook and trying to fight for his life. And I have had more than 10 of those pikes in my life, so that I first had a small fish on a small lure, and then a big pike comes in. Yeah, so that's my small fish on at the end of the line. Okay, but that's basically, you can do this system with any microcontroller. Any will do. Any 8-bit low power. What makes the Cypress processors different is actually that they have the capacitive sensing capabilities. For example, the original iPod had capacitive sensing technology from Cypress directly. Okay, and well, capacitive sensing is basically the easiest capacitive sensor is the comb kind of structure, where you have 2 electrodes like that, and basically they're not connecting but makes a capacitor. And if you have some change in the electric property, here's the permeability of the material here, it changes the capacity. So it's variable capacitor actually. No, well, yeah, kind of sort of. So it senses the changes of the environment based on the capacitance. Okay, here's a plate. Or actually, originally I just put the plate here, so that is open. And underneath I have that the capacitance structure right here. And measuring the capacitance, the microcontroller knows that, okay, now this is on water, I can start the power consuming the vibrator operation. So it's fishing mode automatically. You don't want any switches or anything like that while you're fishing. You just want to do fishing. Okay, that's why we are now teaching with the Cypress PSOC systems. Okay, nice story, right? But actually, Cypress systems are not that bad for anything. All of this capacity sensing is just one module from the big selection of modules for the Cypress processors. So basically, the programmable system of chip consists of a microcontroller core plus digital programmable logic circuits, basically. And then it also have analog programmable circuits. So both analog and digital blocks that can be combined so that instead of just one single microcontroller with peripherals outside, you have everything already inside. For example, A to D converter could be there. They also can be the communication devices, serial communication devices. It even can have analog filter inside. Okay, that's something that none of the other microcontroller manufacturers can actually provide on one single circuit. And of course, it also has the microcontroller core with the all kind of stuff there. And of course, a really flexible GPIO. In practically, there are for the digital I/O, there are no really restrictions which pins you can use. So digital I/O, you can use any pins. For analog I/O, you can use only a couple of ports, but that's already a lot of flexibility. Yeah, of course, yeah, there's analog multiplexers to make. For example, you could do an 8-channel the data acquisition system in one chip with communication and everything. Okay, so basically this has inside everything that is needed for one simple the embedded system device. Usually you don't need much of any external parts, just the microchip. Maybe bypass capacitor for the power and the power itself. But anyways, it's very, very flexible kind of and powerful for all kind of stuff, especially for the educational purposes. You know, I hate the kids when there is a microcontroller board and then some, like Arduino, it's just some shields. You stack it that way and you can still do what you wanted. But anyways, this one, that's the whole stack. It doesn't need those shields. Other than, you know, maybe some connectors if needed. But anyways, so let's go back to that one. So that's why we have the Cypress programmable system chip. Yeah, we don't have the study trip. This is wrong information right now here. But anyways, and the instruction labs are not on Thursdays. Okay. So today's topic is about sensors. And I like sharing, like my dear colleague Sakari Lukkarinen, who has been on Sakari's class. You have been on Sakari's class. And he made a really excellent review of sensor technologies. I didn't have anything to change. Well, maybe some fonts. And and I also updated a couple of small bits, but anyways, wonderful information that, so I'm sharing it as alike. Okay, so first of all, sensor. Well, they sense, say, anything like temperature or pressure or humidity. Those would be the atmospheric kind of or meteorological measurements. It can also sense if it's on the water or not. Capacitive sensing means that actually those touch screens and that kind of things. They are capacitive sensing. So whatever you need, you need sensor if you need to sense something. Fundamentally, the main characterization is right there. Then there are some bits and pieces, but anyways, most important characteristics that characterize the sensor are first the transfer function, which actually gives the mathematical formula how to interpret the data. Okay. Sensitivity means how sensitive the device is, how small changes you can actually practically measure. Span or range. Span means what is the usable range of the sensor. Accuracy, precision, and tolerance. All of those three are different things. Basically, we should talk about inaccuracy rather than accuracy. Inaccuracy means basically that how close to the real value you can sense. There are some things that comes from the physics that say that it never can be accurate. Tactile switch is actually accurate. It's either on or off. Okay, but any other sensor has some inaccuracy. Precision is a different thing. It basically it's about how precisely it always gives the same value on the same the environment. Tolerance, okay, that's tolerance against the external changes. Then there's of course calibration, a calibration error. All the sensors in principle should be first calibrated without before using, and then the calibration is never really accurate. That's why we need a calibration, but we have a whole section about the calibration later. Oops. Hysteresis. Hysteresis from physics. For example, ferrite materials has hysteresis. It means that when the signal is going up, it goes different way as it goes down. Okay, so it's basically the output somehow has a memory of the previous values. That's basically what it is. Non-linearity, well, in a perfect world, everything would be linear. That would make the calibration very simple. You just need 2 points and draw a line, and that's your calibration. But unfortunately, nature is always non-linear, so we have some non-linearity. The saturation, okay, a good example of saturation is measuring a temperature with any device. For example, one old-fashioned the mercury thermometer. Mercury freezes at -18 or something like that. So that's the lower saturation level. Then it starts boiling at 100 and some. No, it's less than 100 degrees. I think it's less than 100 degrees. But anyways, it starts boiling at some point. Okay. That's why alcohol is better. Just kidding. Well, alcohol is less toxic. Okay. Repeatability and deadband, okay, those are also something. So repeatability is, how well it actually does the same thing all over again. Deadband is also about if there's a gap which never actually occurs on the sensor. Resolution. Resolution is more about the digital circuits. It just gives the how big is the quantization level. So what is the value difference between 2 bits? Okay, then electric properties like output impedance, that's basically part of transfer function, well, output format, operational characteristics, and dynamic characteristics, that kind of thing. So those are basically the sensor characterization. And if you take any sensor, there are also plenty of other things that's been measured from the sensor. Okay, a little bit about the transfer function. So the definition is more like that. The transfer function represents a relation between stimulus, meaning that something happens, like when you're measuring the temperature, it's fundamentally, if you are measuring air temperature, about the molecular movements of air molecules. That's how temperature actually is showing up in the physical world. That's the stimulus. It does something for the sensor material what you are using. And basically it's between stimulus and response. So when you put a stimulus on a sensor, then it responds. Otherwise it's not a sensor but a dead rock. And that basically the transfer function says what the output is when you have this kind of stimulus. Okay, this is quite nice. Physics is about finding the transfer function, but engineering requires the inverse transfer function. So we are trying to figure out from the response what is stimulus, not the other way around. So basically this transfer function, the inverse transfer function, is the key to get to the data later on. And we will be coming back on this one on the calibration. Okay, one example of the transfer function is the thermistor. Usually the negative temperature coefficient kind of NTC thermistor, which basically has quite in a short range the transfer function is quite linear. So for certain change in temperature, the resistor changes certain amount. So and the K is the basically just the calibration coefficient, one single coefficient. And negative meaning that K is negative. So for a positive temperature change, the resistance goes down. Well, there are plenty of materials which does that one. So when you have higher temperature, basically you get more free these what are those? Free electrons and also the in the semiconductors you also have holes, so you have more this yeah. Hmm?
You mean N and P region?
Hmm?
You mean the P and
Yes, yeah. So you need you get more of these charge carriers. Yes. More charge carriers, which means the resistance goes down. There's also PTC. When you heat this material, it actually does the opposite. So there's less charge carriers. Both thermistor kind of types exist. So if you are looking for a thermistor type of the sensor, you need to be quite careful when you are selecting it, that you have is it NTC or PTC, and then also what is the range where it actually functions. And the range where it actually functions means that where is that first approximation actually valid. Because that second one is it's the exponential characterization that's more common basically when you are in a basically in, let's see, above about 50 Kelvin and above up to the plasma stage. Basically, those materials, the resistance or the conductivity is based on the number these charge carriers, and basically that's what usually happens. So basic well, it follows an exponential curve. Okay, it follows an exponential curve in quite wide range. So let's see. Does it go like that? No, it goes like that. Okay, so exponential on with the negative b. Yes. Anyways, the first order approximation means that when you go into very short region here, the difference between exponential and linear will come negligible. Okay, but if you are measuring wider range of the temperatures, then you basically need to use that so-called Steinhard equation, which is the inverse solution, one of the inverse solutions of that exponential form. Okay. Yeah, I have swapped the axis here, but anyways, that's also. I think that plot there shows a real NTC resistor, the output versus the or actually that looks like a, if input is between 0 and 12, it probably is just a simulation of some sensor. But anyways, that's how they usually do. They are close to that, some calibration curve or the transfer function, but not exactly. So the sensor, or using sensors, it's very hard of practical physics. It's experimental science. And why we need these transfer functions then? Well, because it depends on the place where you are using the sensor, how accurate results you actually need. That actually defines what kind of approach you would do to get the inverse polynomial. But anyways, I'll leave the rest of that one to the calibration section. Then we definitely come back to this. Okay. Then this sensitivity, defined as the first derivative of the transfer function, meaning that how big change you will get on the output when this input changes some things. And then there's that some NTC thermistor type 203E3. Okay, doesn't say much to me. 20 kilo ohms, and then that E3 gives the sensitivity, I think. Okay, but anyways, as you can see, it's exponential curve, which means that sensitivity also depends on in which part of the curve you are. If you are on a linear path, then the sensitivity is more or less constant during that one, on that linear path. Okay. Span, full-scale input. Yeah, I already explained that one. With the the old-fashioned thermometer. But the same thing goes with all these electronic devices. By default, the electronic devices work in room temperature, period. Commercial range is from 0 degrees to 40 degrees. It's not wide range. Car manufacturers have their own range. Not Finland to not Sahara. Okay, so span actually depends on the technology used. The NTC thermistor itself, the span is for that one is marked from -40 to 125 degrees. Semiconductors usually start having non-reversible changes at 200 degrees Celsius. And then also the structure will start to brittle below something like -100 degrees. But you know that covers quite a lot of area already. Okay. Smart sensors have a problem with these the other electronics than the functioning of the sensor itself. Okay. Then, all right, what is the accuracy, precision, error, and tolerance? And those pictures more or less tell everything, but anyways, the accuracy is the highest deviation between the true input and a value present by the sensor. Highest. Okay, I think those are still measured by some statistical methods, so it basically means the root mean square error, which is basically more or less the highest error. Okay, precision. Basically how well you can calibrate this sensor, how precise the values will be. Error is simply the difference between the true and the measured value. Tolerance, okay, this is the manufacturing kind of term. Tolerance gives the accuracy of these or how much the values in average differ from sensor to sensor. So you take 1,000 sensors, and that's actually a statistical measurement. So if this is the nominal value of that, for example, a thermistor 20K thermistor, and if you have, for example, 2% accuracy, it means that Six sigma number of the values will fall into plus minus 2% range. So most of them actually are on that one, but this is statistical measure. So in 1,000 pieces, you probably have 1 or 2 that are not fitting this 2% range. 6 sigma is about 0.001, so it's 1 over 1,000, I think. Sigma is here just the standard deviation of the curve. Okay, so that's how the manufacturers are actually using on their tolerance presentations. Oh, yeah, here's the accuracy and precision. accuracy actually has some noise on it. And precision just means how well those values are fitting the same spot. That's an excellent picture. So if you do some shooting practice, you shouldn't, I think, but unless you are hunting, then you might actually do some practice shooting. Okay. Yep. Precision. So giving the same result all over again. Accuracy. You may have a very accurate sensor, but the values are varying, meaning that you need to do some averaging of the results or something like that. Okay. Okay, one more thing about this. So how to actually improve the systems. If it's accurate but not precise, then you can start doing statistical methods to actually get a better accuracy. On precision, you basically need to do calibration. Okay, more pictures. The deviation, or earlier it was thought as an error. The deviation is the especially on the calibration. Well, the deviation is always the difference between the true value and this estimate value. On a sensors, it practically means you have the actual curves that you do not know, and then you have the calibration code, calibration curve that you think it's okay, but there's also always some deviation. Just terminology. And well, there's actually a small mistakes about the highest deviation is not accuracy, but it's inaccuracy. Okay. Small example. Linear displacement sensor. The easiest linear displacement sensor is actually a linear resistor. Just a slide. You have seen those on your grandfather's audio equipment, sliders. It's basically just a variable resistor where this slide is the same as that button that goes up and down, and then at the one end you have the reference voltage, and on the other end you usually have the ground, and that one actually here gives the ratio of how much you have here, resistance here, divided by total resistance times Vref. Okay. So linear displacement sensor, 1 millivolts per 1 millimeter. Displacement transfer function is simply a single slope, but okay, 10 millimeters would provide 10.5. Okay, 1 point calibration, you can actually then do that kind of math. So okay, it says inaccuracy of 0.5 millimeter and so on. So it's just plain engineering math to calculate those things when you have done the checking the how well this device actually works. But I think this, again, we'll visit this one later on the calibration, and we actually do some of this stuff in real life. Oh, by the way, the easiest rotation angle sensor. Yeah. How about multiple turn? Yeah. Why not? It works. And if you have ever thought that how come these small servos you can find very cheap, and they are measuring the angle, rotation angle quite high accuracy. Well, very cheap sensors. The inaccuracy actually on the data sheets, if you go to the sensor data sheets, there are different ways to show them, and sometimes it's given in terms of the measured value. This is true especially for the for digital sensors. Those are pre-calibrated and they basically give just one number, which is the highest deviation or typical highest deviation. These highest usually are the Six Sigma values, the statistical values, or percent of the input span full scale, yeah, or percentage of the measured signal, or absolute error on the measured signal, or terms of the input signal, the output signal. Okay, so different kind of. So it's quite hard to make actually good comparison between two sensors if they do the same thing but the different manufacturer. Okay, calibration error. Well, yeah, that's basically the error on the transfer function. Then about the hysteresis, this is about the output doesn't follow exactly the input, but it has some memory effect from the last values. Like in temperature sensors always have that one. They have mass. The lowest mass temperature sensor is made by Vaisala Corporation in Vantaanlasku. So it's about 10 micron thick wire of platinum. So it's 1/10 of a hair, and it's about 1 millimeter long. So not much of the this heat mass there, but still some heat mass. There's also a story about that one. Maybe I will tell you later. Okay. The non-linearity error. Okay, if there's a non-linearity, that's also considered as error, and that's usually it's given by the maximum deviation from the linear curve. Saturation, that actually given by the gives the where the sensor is linear. Okay, when the sensor saturates, it does not mean that you cannot make any measurements anymore. You just have to calibrate correctly. Sometimes it takes some experiments and also some modeling. Okay, real life example. Let's take real life example just for fun. Photomultiplier tube is still the fastest and best way of measuring very, very weak light signals mostly. So single photons. Light is made of photons. That's the photon is basically a quantum of light that has exactly that energy is just constant times the frequency. Very short amount of light, but anyways, that's when you get into very low signal levels, you need to start counting photons in physics. Sometimes even in real life. But anyways, if you get lucky, or not lucky, if you get smart, you put some, say, metallic like gallium is it K? Calcium is Ca, and gallium is Ka. K. Gallium. Okay, gallium. I don't remember it anymore. I used to be a physics. Okay. Okay. So, but anyways, you get a anode made of the gallium. Well, maybe I should make a cross section of it. All right. So you have a anode here, which means that it's highly negative. So it's minus V voltage here. The operating voltage hits a gallium surface on a vacuum, which means that if this quantum is high enough, it actually electron will come out of the surface. So it's not on the material anymore. You can grab it actually using a this is more positive dynode here that starts traveling there, hits the dynode, it multiplies it. Because you are actually accelerating the electron, it hits and releases the energy into this material, and then basically you get the 2 or more electrons, and then you can have a chain here, acceleration chain, and finally you have even a microampere pulse of current coming out. Microamp. Okay. Roughly. With some good tubes, you can get it to almost a milliamp level. But anyways, when you need to measure very low light levels, like only a few thousands of photons a second, then, for example, in astronomy or deep sea research, or there are actually plenty of things where they use it. On CERN, they have something like gazillion of those kind of sensors. Okay, so this one actually has tendency of saturating, meaning that, well, physically the later dynode starts to, so they cannot give any more enough of electrons, and basically some of that, when you have higher energy here, it starts to just generate heat, and you start to heat the dynode, and it doesn't anymore release that much electrons. It starts at some point saturating. So very linear to the end, the saturation. So it's exactly like that one there. Exactly like in this picture. So it starts saturating. Normally, that's where you stop measuring. But if you really have to have very wide dynamic range, more than 100 dB. So if you want to measure very, very small amount of light with the same experiment as you are actually using 10 to the, let's see, 100 dB is 10 to the 5. 10 to 5 more light. And still have measurements, so not just guesses, not just nice pictures. You actually need to do some measurements and modeling of the saturation, and you can even go, since this at some point this saturation starts going down, which means it doesn't give any pulses anymore. You can even go up to this point with some tricks. So a tube which was rated as let's see, 300 megahertz tube, meaning 300,000 photons per second. I have tuned that one up to 1.4 gigahertz. Yoo-hoo! In good old days. I know. I don't know gig. Just a trick. Okay. And we had a need, atmospheric research. So basically that was needed on a light radar, meaning that on the lower atmosphere you have plenty of particles that, or you can actually have even a cloud there that reflects the light really well on lower on the near range, and then when you go to the as far as you can actually have anything there, so 24 kilometers, you still want to see if there are any particles there. So from the lower troposphere to up there, you need that 10 to 6 dynamic range. Okay. Repeatability, deadband. Okay. The repeatability is kind of it's part of the hysteresis kind of thing. So when you go measuring the same characteristics on different routes, you will get a different value. The deadband is quite normal for a multi-sensor systems. When you, for example, you have different sensor for the positive and different sensor for negative values, or there's some limit. This resembles the same thing as on old B-type amplifiers. Okay, resolution again. Smallest increment in input which can be sensed. Okay. And basically resolution is usually given for the digital sensors, not analog, since in analog you have this accuracy and precision. And accuracy you can actually improve with the averaging kind of or filtering, and precision you can do calibration. But the resolution is what it is. You cannot improve it. It's just resolution. Okay. And then output impedance is just as you probably have heard from the circuits classes. So basically the output impedance and the interface circuit input impedance, you'll get some loss of signal on that kind of circuit. Okay. All right, now we are talking about the output format. So basically output format characterization, it's just read the manual. Take a look at the sensor data sheet. The output can be basically anything. There are no given rules it must be like that. There are some industry standards, like for example on the current mode sensors, meaning that the output is actually a current signal. There is a 4 to 20 milliamp standardized signal there. Then there's another standard which is 0 to 20 milliamps, which means basically that the sensor should give values linearly related on that range. The span of the sensor is fixed with the span of that output. Okay, FM, yes. Capacitive sensors. The first capacitive sensors used in big scale were on the radio sounds, and basically this is, well, one capacitive sensor looks like that. uh, on a glass tube of very thin. It fixed on this location, a special glass, and those are the platinum wires, very close to each other, almost touching, not quite touching, but almost, meaning that there has been a wire which has been just lasered off. Temperature is actually changing the distance enough to be measured. So that actually also is a capacitive sensor. And capacitance, if you have capacitance and you have inductance, what do you have there? You need just the excitation, and you have an oscillator, feedback and excitation. And basically you can measure the capacitance based on the frequency, fundamental frequency of this LC circuit. Okay, now we are talking about radiosonde, which is a single-use instrument, high precision single-use instrument, which has been calibrated independently on a calibration chamber on different temperatures, humidities, pressures. And this is the way to do it cheap, since you can have these different capacitors for temperature, pressure, humidity, and then you have just a multiplexer to multiplex different capacitances to one single oscillating circuit, and then you have actually frequency that you can then modulate with the radio frequency, and there you have radiosonde. And the list price is less than 100 euros each, single-use instrument. Okay, that cannot cost much. It must be very simple. So that's the way to do it, simple. And that's the 1 millimeter long, the platinum-based temperature sensor, but not measuring the platinum temperature, but actually to measure the distance. Okay. So yes, FM it can be, and it still is. Although these are now mostly these radiosondes are now digital transmission, but they are still making these old-fashioned analog. And yes, they are analog. There's only a switch to a timer and a switch to go through different capacitances. Okay. Yeah, other forms, PWM, yeah, can be proximity sensors like ultrasonic. Ultrasonic is a pulse period. It's the pulse. In principle, it's a pulse width modulation. What it does, it periodically sends the pulse, and then basically the reflection is just putting there a peak. So it's in principle it's a PWM, or like pulse time modulation, I think. Okay. Amplitude of signal, that's the most common usually. It can be even phase, polarity, or signal shape, time delay, digital code, whatever. You just any signal will do as long as you can interpret it. Okay. So excitation. Now we get excited. So yeah, I know. Almost all sensors need some excitation. It's not too often that the sensor can be, the signal can be directly used. Well, like how you measure resistance. Resistance, in principle, there's only one way to do it correctly. It's the Whetstone bridge. Okay, you read more from the literature about that. That's how you measure the, if you need to measure some resistor electronically, then, well, multimeter does it too. So it's actually just put that one as the device under test, and it's a Whetstone bridge inside. So there's excitation of voltage. Capacitance, okay, that's one way of exciting it. So it's an electronic that makes this as a part of a oscillator or part of an integrator. So that's the way to excite. So basically it's a kind of the power which is needed to use the sensor. Okay, one sensor, for example, audio. These cheap wired microphones for PC, which goes into that headphone kind of thing. That's a ceramic, usually ceramic, the microphone, which is simply a capacitor which requires some external voltage to get anything out. Okay, because, well, you have that's the microphone. Those are big membranes. One is solid, one has holes so that the air can go through. But anyways, you have usually a excitation voltage here, and this goes basically a some sort of way to measure the current, and the distance changes, meaning that changes the capacitance. If you have capacitance change on constant voltage, you have a current. Right. So there you usually have a one transistor and blah blah blah, but that's something you can find from any electronics book, a good one. How that one, but it requires, meaning that if you have a PC, you have that audio jack. By default, it's designed so it gives the that excitation voltage to a capacitive microphone. Then, actually, by software, it changes it to something else if there is active. Well, this voltage, although it's usually say about 10 volts or so, but there's absolutely almost no current on it. So the electronics is designed that way, so it doesn't give much current. Okay, just the excitation voltage. Good. But any active sensor, you need the power. Some of the digital sensors actually can take the power from the data line, but not all. You usually need the power. And the sensors are also usually stupid ones, so if you reverse the polarity of power, you have smoke. We used to, 10 years ago, we used to have these electronic classes, a lot of them. And we had one class that we ordered some annual something like 120 sensors, because, well, they're just, less than €1 each, something like 10 cents each, because we knew that half of the students will try which way it goes by, just trying it, not reading the manual. Oh, great, that was fun. Yeah. Okay, but there's only one way to learn electronics or any practical matter, the hard way. Okay. So, okay, now just a small word about the dynamic characteristics. So basically the dynamic characteristics is also one part of the transfer function. So transfer function actually should also give the how the output depends also on the time. but here we are in a kind of luck, since most often any sensor characteristics is more or less like a first order low pass filter. So very simple to model. It's also doable to compensate for that kind of the dynamic errors. All right. There's even a source. Good. Let me take a quick look what we are going to do next. So it's program system chip fundamentals. Okay. So that was basically the my first part of this, and next week, as I told you earlier, will be flipped, meaning that I will post their video that you can watch before coming here. It will be boring, of course, but well, sometimes life is. Get used to it. Otherwise, let me close this session.